I'm Zhang from BUPT, and today I'm really glad to present our work, More is Different, prototyping and analyzing a new form of edge server with massive mobile SoCs. And this is a joint work with a lot of collaborators from BUPT, Tsinghua University, and vclusters. So let's start. The high power consumption is a persistent and historical issue in nowadays data centers. And there are a lot of resource-consuming workloads, such as large language model training, big data analytics, and video streaming, and they all make this issue more severe. So how to build energy-efficient data centers? And we think this can be done at the software level through resource virtualization, load balancing, or we can update our hardware with the RISC architecture and lower process nodes. So in this talk, we want to discuss the selection of the hardware selection in edge platforms by comparing the key factors with the cloud. And the first is the locations and spaces. The cloud data centers are usually located at the cherry-picked locations, and their spaces are very large, while the edge platforms are typically near population with limited spaces. So considering their locations, the cloud data centers usually have abundant and cheap power supplies, while the edge has constrained and expensive power supplies. The cooling facility is also different. The cloud data centers have the cooling facility are well built and can provide powerful cooling capabilities, while they are weak or even missed at the edge. And as for the workloads, the cloud data centers will receive multiple types of workloads that are more stable and predictable, while at the edge, the workloads are more specific and highly variational. So what the hardware should be like at the cloud and at the edge? And in cloud data centers, the hardware are mostly constructed with monolithic servers that have many QCPUs and domain-specific accelerators like GPUs, TPUs, and FPGAs. Edge platforms can directly inherit such hardware used in the cloud, but we believe that these monolithic servers can't meet the requirements of the edge platforms because they usually operate under different locations than the cloud environments. So now the question is, what the hardware should be like at the edge? And in this study, our answer is smartphones. The intrinsic of using smartphones at the edge have the following benefits. And the first is their higher energy efficiency compared to traditional data center servers. And this is because these mobile processors are usually use the ARM architecture and designed for the battery-operated mobile devices with intermittent usage patterns. And the second is that these mobile processors are usually heterogeneous with mobile GPU, NPU, and video codec. And these coprocessors can provide us to run both the general purpose workloads on the CPUs and the domain-specific workloads on the coprocessors. And the third but not least is that the smartphones have the ability to run the mobile operating system and applications. And this feature allows us to run one killer workloads, the mobile cloud gaming. So mobile cloud gaming allows us to enable the WinP mobile devices to run the immersive, resource-consuming mobile games released in recent years. And such services have gained the business success. And one of the most popular games, the Genshin Impact, has gained more than $5 billion USD income dated to February 2024. And its cloud gaming version downloads has reached more than 1 million, updated to this month. And the underlying rationale of using the smartphones to support such mobile cloud gaming services is that these mobile games are optimized for the mobile platforms and processors. And if you are interested in the mobile cloud gaming services, don't miss our final talk of the edge computing session. So it's not a new idea of putting a lot of smartphones in the cloud. And there are a lot of cloud providers. They have built physical smartphone farms, such as the AWS device farm and Google Firebase device farm and Douyin device farms. However, these smartphone farms are used for providing the mobile environment for testing purposes. And in this study, we propose to grouping multiple individual mobile processors at the edge by removing the burdensome screens, battery, and provide direct power supply and Ethernet to them. And this reduces the space usages and enables a more dense computing unit integration at the resource-constrained edge, and enable more stability and higher energy efficiency. So the left figure is a commercial SoC cluster, and it can hold 16 mobile SoCs within a 2U rack. And the server has been largely deployed in the Alibaba edge clouds, and it currently supports mobile cloud gaming services and cloud services. And this is a conceptual architecture of the SoC cluster. And we can see that there are every 5 mobile SoCs are integrated into one printable circuit board, and this is customized. And there are 16 mobile SoCs in total inside of the server. And the next is the networking units. The networking units is one backplane to connect all the PCB boards and all the SoCs to a 20 gigabytes Ethernet switchboard. And the next is a baseboard management controller, and it can provide the SoC PHB control and the thermal management inside the server. The last is the cooling devices as the most servers, because cooling devices can make these mobile processors to unleash their full performance unlike they operating in user smartphones. So although the SoC cluster are widely deployed in edge clouds, their hardware usage are highly variational. And through our industry collaborator, and we obtain the real-world network traffic of an in-the-wild SoC cluster that only serves mobile cloud gaming services. And you can see the results in the figure, and it shows that there is an up to 25 times the outbound traffic gap, and this drives us to explore more general workloads at the edge to fulfill them in their idle time. So before we go to the end-to-end edge applications, and we use one cross-platform benchmark, the Geekbench 5, to conduct macro benchmarks to compare the CPU performance with other servers. And here we select different hardware, including one traditional edge server with Intel Zen 5 series GPU with 40 cores, and the 2 cloud instances, including the AWS Graviton 2 and Graviton 3. And the SoC cluster used in our study is consisting of 16 Qualcomm Snapdragon 865 mobile SoCs, and it has 480 cores in total. So let's first look at the procure performance, and we can find that the SoC cluster aligns closely with the traditional Intel CPU server and outperforming the AWS Graviton 2 instance, but not matching the performance of the AWS Graviton 3 instance. For the whole server perspective, and we can find that the large number of SoC CPU cores can deliver superior performance compared to other CPU servers. So, except for the macro benchmarks, we extended the benchmarking using 2 more typical edge applications. And the first one is video transcoding, and we categorize it into the live streaming transcoding and archive transcoding. And we use the FFmpeg and later Android Media Codec to test it. And we selected 6 videos from the vBench and report the metrics like throughput, energy efficiency, video bitrate, and video quality. For the deep learning serving, we selected the best performing libraries on different hardware, including the TVM on Intel CPU, TensorRT on NVIDIA GPU, and TF-Lite on SoC clusters. And we use 4 models, including both the floating point and the quantized in-point models. And we also report the latency, throughput, and energy efficiency. We selected one physical server consisting of the Intel Zen 5 series Golden processor with 14 CPU cores and 8 NVIDIA A14 GPUs. And we also selected one top-tier data center level GPU, the NVIDIA A100. So in the video transcoding benchmark, we first want to answer the question is, how much energy efficiency can be gained by using SoC clusters for video transcoding. And first, we will select the live streaming transcoding task and use the number of streams a single watt can support to represent the energy efficiency. And the result is shown in the figure. And we can conclude that the SoC CPUs are up to 3.2 times more energy efficient than the Intel CPU, and up to 4.5 times more energy efficient than the NVIDIA A14 GPU. But things seem different in the RQ transcoding tasks because they require more computation compared to the live streaming transcoding tasks. And we use the number of frames a single jar can support to represent the energy efficiency. And the result is shown in the figure, and we conclude that the SoC CPUs can still achieve higher energy efficiency than the Intel CPU. But the SoC CPUs only outperform the NVIDIA A14 GPU in simple videos like V2 and V4, but fails in more complex ones. So the next question is, to what extent do SoC codecs outperform the SoC CPUs? So we use the live streaming transcoding task and report the throughput and energy efficiency also. As for the throughput, this figure shows that the SoC hardware codecs can deliver up to 3 times throughput improvement over the SoC CPUs. For their energy efficiency, especially on the simple videos like V1, V2, and V4, the SoC hardware codecs shows a geometric mean of 2.5 times performance improvement, while for the complex ones, it can deliver a higher gains, ranging from 4.7 times to 5.5 times improvements. And this indicates the huge potential of running the live streaming transcoding tasks on SoC clusters. And the next question is, with such good performance and energy efficiency, but can SoC hardware codecs can deliver satisfactory QoE in live video streaming tasks? And in this question, we use the video quality and video bitrate to represent it. And the first figure is showing the video quality, and our conclusion is the videos transcoded by the SoC hardware codecs show up to 15% lower PSNR values, and this means the videos compromise in video quality a bit. As for the bitrate, and we can see the SoC hardware codecs struggle to meet a relatively low bitrate cap, like we can see in the V2, because the red dashed lines represent the target bitrate. So we can observe the inconsistency in video quality and video bitrate of different video codecs. So this wants the edge service operators, they should judiciously select the appropriate hardware to meet the application QoE if they're using the SoC clusters in live streaming transcoding tasks. The next question is deep learning serving, and we only show one question that people may concern, and this is the inference latency. So the question is, can SoC clusters support deep learning serving workloads with low latency? Because the latency is a critical factor in delay-sensitive workloads. And in our experiments, we set all batch sizes to 1 on different hardware, except on the NVIDIA GPUs, because they are so powerful. And our results show that the SoC DSPs could deliver adequate latency in medium-sized DNN, like nearly 9 milliseconds on the quantized ResNet 15 using SoC DSPs. Well, the SoC clusters challenge to handle large models with individual SoCs. For example, the inference latency of the ResNet 152 is nearly 270 milliseconds, and using the SoC CPUs. The quantized ResNet 152 may take nearly 20 seconds, but it is still longer than processing 62 samples on a server-level GPUs. The second question is, if the latency using one SoC for deep learning serving is high, how about we involving more SoCs to collaboratively run deep learning inference workloads. And in this experiment, we use the ResNet 50 model with the floating point and two approaches. The left figure is a tensor parallelism proposed in CoH, a previous work, and the right figure is a tensor parallelism with computation and communication pipelining, and this is our initial attempt to optimize this. And we find that involving more SoCs doesn't proportionally reduce the inference latency. And even with the optimized software stack, the network communication time could still contribute to more than 20% when using 5 SoCs. So as we do a very simple attempt, we just conclude that the software enhancements like more fine-grained tensor parallel partitioning algorithms and hardware optimizations like improving the network bandwidth between each SoCs should be utilized jointly. The last section is the SoC longitudinal study, because in the evaluated SoC cluster only contain one specific SoC model released in 2020. So we want to expand our results to more SoC models. So we select 6 Qualcomm Snapdragon 8 series SoC models released from 2017 to 2022. And also the 2 workloads, the deep learning serving and live streaming transcoding. And we report the latency and throughput. And the table shows the smartphones we used. And the 2 figures shows our results of latency and throughput in deep learning serving and live streaming transcoding. And we can observe a tremendous performance improvement in the past 6 years of the mobile processors. And there is a significant performance boost in the SoC DSPs. For example, from the 845 to the 8 plus Gen 1 version, the improvement could up to 8.4 times. And the gradual improvement and the gradual performance improvement on both the SoC CPU and hardware codec not only attributes to the hardware improvements, but this can be also attributed to the Android OS upgrades. So we think the mobile SoCs are promising candidates for more complex server-side workloads in the future. But we think the most important thing is to leverage the coprocessors to fully unleash their performance. So let's conclude. And the first is common sense, and we think it's common sense, is the energy efficiency is critical to the edge platforms. So in our work, we propose an extreme design towards the energy efficiency SoC cluster. And each SoC cluster consists of multiple low-power mobile processors, and each SoC is inherently heterogeneous with CPU, GPU, NPU, and video codecs. And such SoC cluster is commercially successful in mobile cloud gaming services, and we want to extend it to more general workloads. So we built a benchmark suite and conducted a set of experiments to demonstrate the pros and cons of such SoC clusters over traditional servers. And more experiments and results can be seen in our paper. Because of the time limit, we can't include them in this slides. So finally, we show the potential of directions of software and hardware level optimizations in the future of the SoC cluster. And our benchmark suite is open sourced at this link. And there is also online access to such cloud phone services powered by the SoC cluster. And you can check this doc to access it. And thank you very much. I'm happy to take questions about this new type of edge server.